Well, good afternoon, everybody. It's great to see the turnout today for our Triggs International Vinifera Lecture Series. I'm Debbie Ingalls. For those of you who don't know who I am, I'm the director of the Cool Climate Enology and Viticulture Institute here at Brock University. Before we start, I'd like to begin this gathering by acknowledging the land on which we gather is the traditional territory of the Haudenosaunee and Anishinaabe peoples, many of whom continue to live and work here today. This territory is covered by the Upper Canada Treaties and is within the land protected by the Dish with One Spoon Wampum Agreement. Today, this gathering place is home to many First Nations, Métis, Inuit peoples, and acknowledging reminds us that our great standard of living is directly related to the resources and friendship of Indigenous peoples. We are celebrating a milestone 20 years of the Triggs series today. The lecture series was first established in 2004, and I'd like to acknowledge Don and Elaine Triggs for their vision, leadership, and generosity to establish an endowment that allows us to bring a leading edge speaker to Ontario to share their knowledge about premium vinifera grape growing. Don and Elaine were not able to join us today, but Alan Jackson, the Triggs' close friend that has acted as their spokesperson for many years during their time in the Okanagan, is here to join us this afternoon. Also, thank you to BASF Canada, who came on board in 2011 to partner with us in order to make the Triggs International Premium Vinifera Lecture Series a truly national event. Through their sponsorship, we are able to bring our speaker out to the Okanagan grape growing industry to present 2 days of collaborative learning. I'd like to acknowledge Bruce Ions, Regional Sales Manager, and Colleen Krunikan, Horticultural Specialists, both from BASF Canada Inc., and they are both joining us here. A few more thank yous before we get to the event today. For those involved with the Vineyard Technical Workshop yesterday, thank you to everybody who was involved. This includes Kevin Kerr, where is Kevin? Kevin's in the back there, for working with both our speaker and our Vineyard site hosts and for facilitating all the discussion yesterday. I'd also like to thank our site hosts, who include Bill and Brian Shank, Matthew Speck from Henry Pelham, who is here in the front, Tristan Bondette and Shiraz Motier from Malabar, and also, again, another special thank you for Henry Pelham for treating us to a glass of wine yesterday with our luncheon. The Grape Growers of Ontario, a big thank you for sponsoring our lunch yesterday. And last but never least is a big thank you to Barb Tatarnit for coordinating this event that we just brought back after a 5-year hiatus. There's a lot involved in coordinating among the sites and the speaker and the travel. So thank you for all of her attention to detail. That makes this just an exceptional event. Today's lecture is live and will be recorded so that if any of your colleagues weren't able to make it here in person today, they can always log on to the CCOVI website and find the lecture. And anybody here that wants to revisit some of the great information I know that Markus is going to be sharing with us today, you can always go back and see that lecture later. And one last reminder, Kevin reminded me of, anybody with a cell phone, please turn it off so we don't have any ringing interrupting us this afternoon. So now on to the intro of our speaker. So Dr. Markus Keller is the Chateau Ste. Michelle Distinguished Professor of Viticulture at Washington State University's Irrigated Agriculture Research and Extension Center in the Pacific Northwest. I forgot to ask you, is there a short form for that? That's a lot in that name. Markus received his master's in plant science and his PhD in natural science from the Swiss Federal Institute of Technology in Zurich, and has since conducted viticulture research and taught in North and South America, Europe, and Australia, as well as we learned yesterday, making many trips home over the years to help his family and his mom with their own vineyard back in Switzerland. His research focuses on how environmental factors and management practices influence crop physiology and production of wine and juice grapes. He is also the author of the textbook, The Science of Grapevines, and I understand it's going into its fourth edition. Is that true? So we'll look forward to getting that released. And he also serves as the science editor for the American Journal of Enology and Viticulture. So with that, please join me in welcoming Markus.
Well, thank you very much, Debbie, for this introduction. It's an honor to be here. It's very nice to be in a climate that's not hot and dry and smoky like the one that I'm coming from. Instead, it seems to be hot and humid here. It's actually a little bit of rain today, which is kind of nice as a change. So I'm not sure what I should tell you today. Maybe we should just go straight to questions and have a discussion, because I told you everything I know yesterday. Those of you who were in the Vineyards yesterday, you already know what I'm going to say. Even though Barb told everybody I was going to change my lecture for today after what I heard today. So that's what I did. I was up all night changing the slides of what I was going to show, which means I have no idea what I'm going to talk about because I haven't seen them before. But no, I thought since yesterday we talked a lot about current issues, things that keep you up at night. Today I would start with the 2,000-year-old quote. And so what you're seeing here is from Columella. Columella was also a textbook author in the Roman Empire about 2,000 years ago. And he had this to say: a vineyard likes, I'm not going to read the Latin version because I don't understand what that means, but I had it translated by Google Translate, and it says, a vineyard likes neither a cold climate nor an overly hot climate, but enjoys a warm climate more than cold. Rain harms it more than clear sky, and it prefers a dry soil over one that receives too much rain. It's almost as if he had foreseen climate change happening a few thousand years later. Vineyards like warm climates, they prefer dry soils, so drought is not that much of a problem. But he also said you should match varieties to the climate and soil. He had that figured out 2,000 years ago. And you should plant high-yielding varieties in warm climates. By implication, that means probably low-yielding or low-cropping varieties in cool climates. So Columella had a lot of viticulture already figured out a long time ago, and we've just been fine-tuning ever since. I've been doing this viticulture research for more than 30 years now, and we're still running up to things that he had already discovered back then. But then if we go, I can move this. So now we're moving to a paper that was published just last year, but about an event that happened even longer ago, about 11,000 years ago in the Stone Age. The current thinking as of last year is that grapes were roughly domesticated at that time. And in two locations, we've always thought the Caucasus Mountains, Armenia, Georgia, those countries were kind of the gene center for grapes and the original domestication center. And they're now saying this is an international team of scientists that spans Chinese, Europeans, and Americans that have been working on this. They're now saying that there was a second domestication center in the Levant, Israel and Lebanon, that area, so Western Asia and Caucasus, which means that if grapes were domesticated in those climates, in those regions, they must be very adaptable to different climates. They must be used to warm and dry conditions, but maybe also to a lot of rainfall. So grapes are tolerant to many different conditions, and that's something that we have to remember sometimes as growers when we despair of it's a drought year or it's a wet year. Debbie was saying, I was visiting with my mother again this year a couple of weeks ago, and she told me that they haven't had more than 2 days in a row this year without rain. Yeah. Downy mildew rampant across Switzerland and in other parts of Europe as well. So when we see these disasters, we have to remind ourselves that grapes can tolerate a lot of adverse conditions. And we have a lot of varieties. So these are the world's top 40 most widely grown varieties. Just 40 that I'm showing you here. They cover 2/3 of the entire vineyard acreage in the world. And you can see a lot of obviously familiar names like Chardonnay and Riesling, Cabernet Sauvignon, Merlot, and Syrah, things that you grow here, and things that we grow in Washington. What this also shows you, this is a graph that splits grapes into climates where they are currently grown. The black bar means cool climates, colder climates, growing season average temperature between 13 and 15 degrees Celsius. And then the red is hot climates between 19 and 24 degrees, average growing season temperature. So you move from the right to the left, and you go from varieties that are predominantly grown in cool climates to varieties that are mostly grown in hot climates. You can see that some of them fit your profile, where you're at right now, mostly to the left of this graph. There are varieties that you are growing, but there are some that you're probably not currently growing, like Green Veltliner. There is not a lot of Green Veltliner in Ontario, but it sits right between Miller Thurgau, Pinot Noir, and Gamay, and so on, the varieties that we do grow here. So those are things to think about for potential varieties to try out, things that might be adapted to future conditions as well. And the mix of varieties in a particular region will probably shift as we get into warmer conditions, in some cases rainier conditions, in other cases in drier conditions. So we will have to adapt what we're planting, and also keep in mind that if you're planting a vineyard now, that vineyard is going to be hopefully still around in 30 years from now, maybe longer. So what we're planting now should be adapted to conditions that maybe occur decades from now. This is back from Washington, where I'm currently working. This is 31 varieties that we grow in a variety collection, all replicated and scientifically up to par. We started doing phenology observations here in 2015. This vineyard was planted in 2010, so by 2015 it was mature enough. We've been observing phenology ever since, and then I'm grouping these varieties from bottom to top, from earliest to latest bud break date. And you can see that, yes, there is a variation in bud break date, but that does not necessarily correlate with the variation in veraison date. So just because a variety breaks bud early does not mean it also goes into ripening early. Concord is a good example. We have a lot of juice grapes in Washington, and it is our earliest variety to break bud, but one of the later ones to start ripening under our conditions. So you can take information like this to start looking at what varieties might be matching our conditions, and then adapt to that available information. Just so you know, we have about a 3 to 5 week variation from year to year in this phenology date. So a lot of variation for a single variety from one year to another. It can be a month difference in bud break date or in the time that veraison happens, and about the same variation, or maybe not quite as much, 2 to 4 weeks variation of the date across varieties. So there's a lot of variability from year to year, vintage variation that gives wine writers something to write about, gives their job satisfaction, but there's also a lot of variability between different varieties that we can exploit when we plant vineyards in different locations, and then can use those different locations to blend, for example, or blend different varieties to get a consistent outcome. Since we're on the topic of varieties, we have used 30 of those varieties over the last 2 years to measure their water status. And in Washington, we have, if I talk metric, about 200 millimeters of rainfall. When we talk Washington, everybody thinks the evergreen state, it rains all the time in Seattle, but we're not in Seattle. We're on the other side of the mountains, and on average, we have just under 200 millimeters, around 8 inches of rainfall per year. So it's essentially a desert that we're growing grapes in. This lends itself very well to experiments like the one we just did here, where we can turn the irrigation water off and let the soil dry down and impose an increasingly severe water stress on these vines, and then we can measure how the vines respond. We had a postdoc, Charles Obiero from Kenya, who was doing these measurements. He would get up at 2 a.m. in the morning to go pre-dawn water potential measurements. Then he would come back and do midday measurements, and he would measure a lot of other things as well in the heat of the day. And essentially all 30 varieties responded more or less the same way to water stress. That was a big surprise for us. Based on the literature, the scientific literature, we had been expecting a big variety of responses. Some of you may have heard of responses like anisohydric or isohydric responses and so on. And in this experiment, that all went out the window. They all responded the same way. All 30 varieties did not feel water stress until the soil had dried down to about 35% of its available water content. This, by the way, is an interesting measure, the available water content. You have to know the field capacity and the permanent wilting point of your soil, and then you can bracket what the available water is, and in between there you can measure soil moisture and translate it back to available water content, which normalizes soil moisture. When you just measure soil moisture in the soil, that is very specific to that particular soil type. And so you cannot really compare across different soils. With this normalization, you should be able to compare across different soil types. So this information should also be applicable to your conditions here. So about 35% available water. When the soil dried below that, all varieties would start feeling water stress. And their water potential, what I'm showing here, is midday leaf water potential. The water status of a leaf would drop below that level until the water just ran out and the leaves were turning yellow and starting to fall off. Yes, Wendy. Are we at questions already? Yeah, we should. Oh, yeah. Sorry. So all the information, thank you for that. All the information I'm showing you from Washington is for own-rooted vines. We have until about 2-3 years ago, we have had 99-point-something% of our vineyards not grafted. That is shifting now, and I will talk about rootstocks a little bit later, but thank you for that. Yeah, so all own-rooted information here. What we found, however, was a difference of about twofold in canopy size. We did not hatch these vines because we wanted to see how they would express their natural vigor in this case. And you can see these two examples that I'm showing you here, Nebbiolo and Turif, on the high end of the canopy size versus the low end of the canopy size. And of course, when you have more vigorous, bigger canopies, bigger varieties, they would dry down the soil faster. And so they would feel water stressed sooner, but not necessarily at a different water potential as these other varieties. So the effect was one of vigor and canopy size, and that is something that you can adapt to as vineyard managers. You can, of course, normalize canopy size, what we've seen yesterday in the vineyard, by hatching, that most of you are doing here. You can just standardize the canopy size, and then all these varieties suddenly behave more or less the same way. Rootstocks, we talked about rootstocks a little bit yesterday as well, and maybe the one thing that I really want you to take home from this is to pay close attention to the work that Jim Wilworth is doing with grower collaboration, testing different variety and different rootstock combinations. We have done the same in Washington, but rootstock experiments are notorious for not being directly applicable to your own local conditions. So you've got to figure out how rootstocks respond under your environment. Just a couple of principles, though. Sometimes we freak out almost about, we need to have just the perfect rootstock for this particular site or for our region. And of course, that rootstock does not exist. What drives water use in a vineyard is vapor pressure deficit. So it's the amount of water vapor that the air can hold that sucks the water out of the canopy and sucks it out of the soil, and that drives water use of the vineyard. Beyond that, it's mostly canopy size. As I've shown you before, bigger vines use more water, they evaporate more water more quickly. And that is determined mostly by the scion. And very little of that effect comes from the rootstock. We don't even really know if rootstocks differ in terms of water uptake. Do they differ in terms of acetic acid production, hormones that they send up to the leaves to respond to water stress? We know very little about that. Water supply, on the other hand, of course, here is mostly determined by rainfall, how much and when it happens. And in Washington, it's all determined by irrigation because we don't have rain in the summer. So rainfall and irrigation determine how much water is available, when that water is available, and then the rest is soil, rooting depth. Across rootstocks, so here, what I'm showing you here in the lower right-hand side, I don't know if I can point here, but I can see what I'm pointing at, so I'm just not going to do that. So the lower right, you can see a graph that's pretty old from the 1990s, from Alsace, from the French wine region, where there were different, comparing rooting depth of different species of grapes that were using as common rootstock and some others. And you can see they're all about the same. No big difference. So we shouldn't fret out too much about, oh, the rootstock here, this one goes a little bit deeper than this other one. Almost all species of grapes have their roots mostly concentrated in the top 50 centimeters to 1 meter. So the soil then determines how much water is available. The rootstock has just a minor effect, and that effect interacts with the presence of nematodes. We sometimes underestimate how much nematodes will have an effect on vigor, on vine size, by how tolerant the rootstock is to nematodes. So it's often not an effect of rootstock on water uptake, but one of resistance or tolerance of nematodes. So what we need is what Jim is doing. We need long-term field trials. Far too many of the experiments that have been done with rootstocks, the things that we think we know, all go back to tiny pot experiments, experiments with tiny pots. And rootstocks and vines behave differently in pots than they do in the field. So we should do these long-term field experiments to explore how rootstocks behave. Just real quick, I put this slide in tonight, actually, because we were talking about effects of rootstocks on wine composition and so on. We did some experiments in Washington, field trials with 3 varieties. You can see Merlot, Syrah, and Chardonnay on 6 rootstocks and own-rooted vines for comparison. And the one thing that stood out was own-rooted vines, which is what you don't have here. With own-rooted plants, we have higher acidity, we have higher pH and higher potassium. So higher potassium uptake by the own-rooted plants that drive the pH up at the same acidity level. All the rootstocks were essentially similar. So it mattered whether the vines were grafted or not, but it didn't really matter what they were grafted to. So very small differences in acidity, no differences in sugar levels, skin, seed tannins, and so on that we measured were all about the same. Own-rooted vines had, on average, slightly higher tannins, but not to the effect that this would really alter our sensory perception in the wine. 10–12% difference in tannins is not very much. So don't worry too much about the perfect rootstock. You just pick one that is available, as long as it's not the wrong rootstock. And then I wanted to say something about grafting itself. When we planted our rootstock trial, it was initially planted as just rootstocks, and then we field grafted, we chip budded on top of those rootstocks a couple of years later, and this was an opportunity for us to look at the height of grafting. And it was mainly because I was new in Washington at the time, and grafting to me, field grafting to me seemed like an onerous task if you do it close to the soil surface. So I said we should also try and graft high on the cordon, so I don't have to bend over so much. That was mostly because I was just too lazy to bend over and kneel down all the time. So we did it at 2 heights, 25 centimeters above the ground, 70 centimeters above the ground. It was a hot year. We grafted relatively late because the year was slow to get started. And then we had this Halloween freeze on the 31st of October, minus 12 degrees. But at the soil surface, it was minus 15 degrees, so a gradient of temperature from the top to the bottom. And sure enough, graft survival was much better at the higher grafting height than at the lower height. We went from 99% take in most conditions to 71% graft surviving the first winter at the 70 centimeter height, and only 20% survived it at the lower grafting level. So big difference in grafting level. This is something to think about, to experiment with. I'm not saying you should abandon everything you're doing now and graft everything at cordon level or at vine head level, but this is something that could be considered to lift the graft union up. Obviously, you're not able to fill up around the graft union that is almost at the wire level. Something else to think about is grow tubes. I'm assuming most of you are using grow tubes when you plant a young vineyard. We are finding that there's a temperature gradient within the grow tube and also a higher temperature range from day to night in the winter. When the sun heats up the grow tube, they heat up the interior of the trunk of the young vines during the day, and then the temperature drops more during the night. So we're finding more cold injury in the winter inside the grow tubes, and we're recommending to just lift the grow tubes up or move them out after the first year. Individual rootstocks, by the way, had no effect in our conditions on scion survival at all. It was just about grafting height, not about the rootstock. Most rootstocks are much hardier, cold hardier than the scions in Vinifera is anyway. Something else that I put in overnight is that this location is important. This is on the left-hand photo. This is a north-facing slope in Washington. You can see a wind machine at the top of that slope. This is at the end of the growing season. You can see that the leaves are still green at the top of the hill and have fallen off at the bottom because it's colder at the bottom. And you also see a lot of growth tubes at that very bottom of the hill where vines have been consistently replanted again and again and again, simply because it's too cold in that lower location of that vineyard, even with the wind machine present at the top. The cold injury can be different within the vineyard, even over very small distances. On the right-hand side, that graph with the phloem, the bark injury that I'm showing you there. This is on a 2% slope, very, very, very small slope. At the south end of the slope in this vineyard, we had a cornfield that they didn't harvest in fall, and then when it got cold, the cold air cooled just behind those standing corn plants. And those plants are maybe 2 meters tall or something, but that was enough to cause cold injury at the lower end of the vineyard, but not at the upper end of the vineyard. So small differences in elevation can cause a lot of differences. So when you select your sites, look for temperature profiles, and also remove obstacles whenever you can, especially if it's in your power to remove those obstacles, then you should do so before you plant or after planting. Wind machines, we looked at a wind machine yesterday. They are very effective if there is a thermal inversion present. So if there is an inversion, the temperature difference from the bottom to about 20 meters up can be up to 10 degrees, and the wind machine can change the temperature at the bottom by about half that amount. So if you have a 10-degree difference, you can raise the temperature at the cordon level or at the fruit zone level by about 5 degrees or so. But when it gets windy, the wind machines just won't work, so be careful with wind. So we talked about winter. I'm going to talk a little bit about temperature effects during the growing season. This is an experiment that we did some years back with Cabernet Sauvignon. In this case, we essentially had a glorified air conditioner in the vineyard. This is work I did in collaboration with Julie Tarara, who was then working for the United States Department of Agriculture with us. And what you can see in the picture, I'm reaching for the pointer all the time. I don't know why, I should just do this. I could use the mouse, but it's not very visible. I'm just going to say what I'm saying. On the picture on the left, you can see on the left-hand side, these shoots are pretty long. On the right side of that picture, the buds have not broken yet. And in the middle, they're just breaking. The difference here is that we were blowing at very low speed. We were blowing either warm, heated, or cooled air on the buds before bud break, just a few days before bud break. And that had a dramatic effect on the time of bud break. It had a dramatic effect on the shoot vigor for the entire rest of the season. So when you have warm conditions during bud break, that will prime your vines to become very vigorous for the rest of the season. This is a vineyard that was deficit irrigated, where we were trying to stop shoot growth by applying water deficit, and that worked in the non-treated control buds. But the buds that had been eating those shoots didn't get the idea. They just kept on growing through the rest of the season. The cooled buds, they broke later, and they never caught up with those shoots, never caught up with the other shoots. So a dramatic difference in shoot growth depending on the temperature at bud break. And you can see what those average temperatures were during that period. That then translated into an effect on fruitfulness of those shoots. A big difference in the amount of fruit set that you can see here. Fruit set percentage went from 45% on average down to 20% from the heated to the cooled shoots. And that, of course, meant a big difference in number of berries per cluster and also in berry weight. So here is one of these inverse correlations. Normally, when you have more berries on a shoot or on a vine, those berries tend to be smaller. In this case, everything was always correlated with shoot figure. Berries on bigger shoots, there were not only more berries, but they were also bigger at the end of the growing season. And they had less sugar in the fruit and lower acidity. This is another case of strange correlation, with lower sugar being correlated with lower acidity, and the high sugar being correlated with the high acidity. And I think what we're seeing here is a combination of the effect of yield, low yield on the cooled shoots, and the delay in development. So they had low yield, they were able to accumulate sugar, but because they ripened during a cooler period of the year, they also had higher acidity. So then we repeated this experiment with a graduate student in Argentina in a greenhouse situation where we applied, superimposed on this treatment, a water stress treatment. And water deficit, water stress during the bud break period completely negated the temperature effect. So then suddenly it became all about water. The vines didn't care about the temperature anymore when they were under water stress. They were just responsive to temperature when the water was abundant, like you usually have in your climate here. But then we took this experiment to bloom time, and we again blew cooled or chilled or warmed air on individual inflorescences. What you can see in the picture is thermocouples wrapped into the inflorescence that are measuring the temperature, and then we were increasing or decreasing the set temperature from the standard. So we still had the normal diurnal range, just like during the bud break experiment, shifting the temperature up and down both day and night on these inflorescences. And the photos on the lower left were taken on the same day after fruit set, all pictures taken on the same day. You can see that dramatic effect again of temperature during bloom time on subsequent development of the berries. First of all, warm conditions speed up bloom time. You know this from your conditions. You have very rapid flowering here because flowering usually occurs during warm part of the year. In Washington, we can sometimes have cooler conditions. Oregon is even worse, where the temperature fluctuates and the bloom time can be extended. In our case, we went 10 days from beginning of bloom to fruit set under the warm conditions, 24 days under the cool conditions. Dramatic difference in the time of fruit set, and then a relatively constant time from fruit set to the beginning of ripening. It's almost as if the seeds need a number of days to become mature, and then they trigger the ripening signal of the berry. That means that if you have late fruit set, you probably will have late onset of ripening. If you have an early fruit set, ripening will start early. Berries per cluster dramatically affected, of course. Fruit set is affected by temperature. So when it gets warmer, from in a range of about 15 to 35 degrees, fruit set usually improves. Outside of those temperature ranges, fruit set drops off. When it's too cool, then the pollen tube takes too long to go down to the ovary, and the ovary is no longer receptive, and then there's poor fruit set. And when it's too hot, the ovary deteriorates very quickly, and you have the same result. So too cool and too hot, same effect, poor fruit set. And outside of those temperature ranges, you're also getting inhibition of cell division, so new cell production during the early berry development period. That will then lead to very small berries. So if it's too hot, we had that condition happening in 2021 in Washington. We had a heat wave right after fruit set, and we ended up with tiny berries by harvest, even though the temperatures afterwards were relatively normal. I'm going from temperature to water again because there's always that interaction between temperature and water. Normally when we have water deficit, the vines respond by closing their stomata. So the pores that evaporate water, they want to conserve water, they close them so that water doesn't evaporate as much. But while they do this, they also inhibit carbon dioxide from diffusing into the leaf interior, so photosynthesis decreases. When the photosynthesis decreases, there is less sugar production in the leaf and less carbon that is available for the fruit. And what I'm plotting on the left-hand side in that graph is a correlation between the daily maximum average stomatal conductance, so how wide are these stomata open between fruit set and verisol, so the average for that period. And on the y-axis, you can see the amount of carbon per shoot in the fruit. So this is how much carbon ended up in the fruit on a per shoot basis, and you can see that there's a direct correlation with how wide the stomata are open before fruit set. And the effect here is because when you have closed stomata, when you have water stress, you get fewer berries on the vine. Often you get less fruit set, the berries are smaller, and they accumulate less sugar if the stress continues during the ripening period. All of that combines to less carbon being produced in the berries per shoot. On the right-hand side, you can see what happens when water runs out on the vines. Here we were measuring the diameter change of berries using small displacement transducers. You can see them in the photo on the upper right. Diameter change of berries. When water runs out, this is during ripening, the berries will shrink. But by the time that you can see visually that they have shrunk, so they show little dimples or something, or the feet are a little soft, not so turgid, by that time you can see that they've already lost 10% of their weight. If you then come and irrigate, the berry size will not recover. It will just remain constant. So you can irrigate during ripening if you can to maintain berry size, but you cannot increase berry size. So this is what winemakers are often afraid of, is you put too much water on, you're going to dilute flavors and aroma components. That is not the case. You're just preventing berries from shrinking. Now back to temperature. We're getting into verisol now, and this is a picture I took in 2022. Now we have a heat wave that was close to verisol. We actually had 25 days with temperatures above 35 degrees Celsius. This was a prolonged, really hot period leading up into verisol, and sure enough, verisol was not advanced under those conditions. It was delayed by 16 days compared with average. So when it gets too hot, development slows down again. And we can see this very dramatically when we look at the east side of the canopy versus the west side. When grapes are exposed to the sun, I will show this later, they're heated by the sun, and so we have cooler conditions on the east side of the canopy on the grapes than on the west side. And in this case, this is Cabernet Sauvignon. The pictures, I took them on the same day. They were nicely ripening on the east side of the canopy, but they were not getting the point on the west side, and we're stuck at the pre-verisol stage. You can see that the right-hand side pictures, those little pictures on the right-hand side, I took a cluster with the face facing west, and the berries are small and green, not beginning to ripen. And then I flipped that cluster around, and you can see on the interior, the shaded side, the berries are ripening. So this is a case of where too much heat inhibits development. What we don't know, what we need research on is quantitatively, how does this work with temperature? We have a rough idea of very high, very low temperatures, but we don't know how does that temperature response curve work for grapes, and what are the underlying mechanisms? What exactly causes these grapes from not ripening at this point? We don't know that, so we need to investigate a little bit more. Something else that I hear a lot these days are decoupling of ripening. How many of you have heard the term? Decoupled ripening. Okay, not very many, so I'm going to tell you about it. This is something that the Australians are telling us a lot, is that if it gets too hot, then ripening is somehow decoupled, meaning that sugar accumulates very quickly, but the acids and the color and the aroma components are somewhat lagging behind. And so we have to keep the grapes on the vine longer so that color and flavors can catch up. But when you actually look at what happens at the beginning of ripening, you find high variability in acidity at the beginning of ripening, and then it all levels off late in ripening. You get very low variability. So there's high variation from berry to berry early on and little variation in acid late, whereas while color, red pigments, anthocyanins are the opposite. Red pigments need sugar to accumulate. The genes that produce the enzymes that produce the anthocyanins, they need sugar to be activated. Without sugar, no color. It's not just that coloration lags behind, like in the picture I showed you before. It's the entire ripening program that does not get started when it's hot. So you have very low variability from berry to berry in color early in ripening. At a level of about 9 to 10 degrees Brix, the color pathway, or the pigment pathway and the cyanin pathway is triggered. And then as temperature continues to change during ripening, it increasingly high variability late in ripening. And this is why you have lots of variation in color, some years with good color, some years with poor color, because the temperatures differ late in ripening, not early. Here's what I was mentioning earlier. This is where we measured berry temperature or cluster temperature in the Cabernet Sauvignon irrigation experiment. On the left-hand side, you can see that the gray line is the ambient air temperature, and then the blue and red lines are the berry temperature. Big variability, and the berries heat up during the day. They heat up by about 15 degrees Celsius. So in this case, the temperature, this is the first week after verisol. In this case, the ambient temperature peaked at 32 degrees, and the berry temperature was 47 degrees. That is too hot. So I plotted here what I would say is the anthocyanin or colored window. Anthocyanins have an optimum temperature range somewhere between 20 and 35 degrees C. They don't accumulate well below that, and they get inhibited or even degraded at higher temperature. So if you have red grapes and you want to maximize color, then your grapes should be within that window for as much as of the time as possible during ripening. But if you grow Riesling or Gewürztraminer or a Muscat with lots of monoterpene flavors, the monoterpenes have a much lower temperature optimum, somewhere between 10 and 20 degrees C. So if you're growing those grapes, then your grapes should be at in a lower temperature window during ripening to maximize flavor compound. This is one reason that Alsace, for example, produces in a cool climate region in France, produces wonderful Gewürztraminers, and we try to do the same in Washington. We get these insipid, not very well. I didn't say that, right? So don't tell any of the wine people in Washington, but they're not so good, right? If I buy Gewürztraminer, I go to a shop and buy an Alsatian Gewürztraminer because it's too hot to produce these flavor compounds. As grapes are exposed to sunlight, not only are they heated, but they also perceive the light itself, and light functions as a signal. Visible light is important for tannin production, important for color and the cyanin production, whereas the UV range of light is important for other compounds like flavonols, sunscreen compounds, for example. So if you have highly exposed grapes, they will produce a lot of flavonols like quercetin, camphorol, those kinds of compounds, and they have a bitter or astringent connotation, which means that if you grow white grapes, Riesling, for example, another problem in Washington is we can sometimes get astringency or even bitterness in our wines if the fruit is too exposed to sunlight. One reason not to overdo it with leaf removal on the canopy with white grapes, for example. And then we wanted to know, this is a question that also came up yesterday, what is more important, temperature or water for ripening? We wanted to know because in the field it's very different or difficult to separate those effects out. You cannot separate light from temperature effects very well, and you also cannot separate water stress effects on a plant from the light effect. So we did this experiment in the growth chamber, high light levels. We took the 10-year average temperature over 10 days pre-verisol and then exposed the grapes to that temperature, daily minimum maximum, 29, 15 degrees. and applied 100% irrigation, full irrigation on these potted vines in this case, or only 50% of water to those vines. So a combination of heat stress and water stress. We heat it by 10 degrees above that average temperature for the heat stress treatment. And then we measured just about everything. When I say we, I mean the graduate students and postdocs that work for me, and I'm just standing here and talking about it. I didn't do any of these measurements myself. What they found was that when you look at the physiology of the leaf, water status, leaf water potential, gas exchange, photosynthesis, and so on, those processes were very much dominated by water, very much less responsive to temperature stress, except when you have a combination of the two stresses together, then the plants suffer the most. But usually it's water that they respond to. When you measure growth, shoot growth, very responsive to water, not really responsive to temperature. That was a bit of a surprise for us. But when we look at fruit composition, it's completely the opposite. Water becomes completely unimportant, you can see on the right-hand side, and suddenly it's all about temperature. So when it comes to grape ripening, what I think now is that the reason that water deficit is good for wine quality is because it leads to smaller canopies and a more open fruit zone and more sun-exposed fruit, and then the fruit responds to temperature rather than to water stress per se. So the plant overall responds to water, and then the fruit responds to temperature. I'm not going to spend a lot of time on irrigation. I actually took out a bunch of slides on irrigation that I had in here. So this is the only one that I will show you. This is just published a couple of weeks ago from a graduate student from Spain who was working on Riesling in Washington, imposing different types of deficit irrigation. And then they were measuring a lot of different flavor aroma components in the lab in wine that was produced from these vines. And the vines from difference in pre-veraison water status of only about 2.2 to 0.3 megapascals. We were a little disappointed not to get bigger differences in vine responses. They did lead to differences in canopy size, again, like I've said before, but relatively small differences in water status. But when you look at these PCA plots, I'm not going to explain the statistics here, but what you can see on the right-hand side is that the different treatments, each replicate, they're completely separated out from each other for the different treatments. So the take-home message from this is not so much about which flavor components and so on are affected, but the fact that relatively small differences in water status pre-veraison, not during ripening. During ripening, they were irrigated the same. Just small differences of water status in the vineyard pre-veraison lead to very pronounced differences in wine flavor, aroma composition, and we measured phenolics as well. There were some differences there, which means that water status, water stress is a very powerful tool to manipulate potential wine style in the vineyard. Now I'm switching back to temperature again. This is just to show you some cool work that many of you know Ben Min Chung in British Columbia now. He was a graduate student of mine and a postdoc, and he did this work as a postdoc. What can we do to mitigate heat stress in a vineyard? We're talking about adapting vineyards to changing climates here. And of course, when you have too much heat hitting the canopy surface, you can try to block that excessive solar radiation, or you can try to remove the excessive energy, right? So you can apply netting, for example, but that's very expensive. In the US, about $12,000 or more per acre. I should have converted that to hectares, but I hear that everybody here talks in acres anyway, so you know what I'm talking about. You can trap heat under the nets. It's inflexible. One put back on again. So netting, not the greatest solution for vineyards. It's very common in tree fruit production in Washington now with different collar nets and so on, but not so convenient in vineyards. Or you can apply water, overhead irrigation to evaporate water and cool the canopy down. But the problem is then you're applying too much water to your vineyard. And then you have that benefit of water deficit gone. What is the effect on shoot vigor? fruit quality, you can have berry splitting if you apply water overhead and so on, or if you apply extra irrigation. So the solution that we came up with was a misting system. We were applying misting nozzle emitter tube that not me, Ben Min, fastened either on a canopy wire, on a foliage wire, on the west side of the canopy, to try and create a fog or a mist on that western side of the canopy that evaporates and cools, but would never hit the vineyard floor. And then 2 years later, we thought, and I can say we now because that was my idea, to put that irrigation system on the drip wire below the vine and evaporate the water up through the fruit zone, because we discovered that the leaves are pretty confident. They don't care too much about water, heat stress and so on. They can operate under hot conditions, but the fruit is the problem, right? The fruit is the issue that gives us differences in wine composition. So we were trying now just to cool the fruiting zone. So these misting nozzles were controlled. We had a leaf wetness sensor installed in the canopy that would turn the misting off immediately when it was getting wet, meaning that the leaves were getting wet. We didn't want mildew, powder mildew developing on these leaves. We didn't want any water on the vineyard floor. So Ben Min installed an infrared thermometer that was measuring canopy temperature across the row of the canopy. And then as the temperature of the canopy increased above 35 degrees, it would activate these nozzles. As the temperature dropped below 30, or whatever we've said would be the threshold temperature, you turn it off again. The result of these different control units was that the system would be on for, say, 10 seconds, 20 seconds, maybe half a minute, and to turn off again for a few minutes, and the leaves would dry, and then would come back on again and try and keep the canopy temperature cool. And you can see the effect here. This is a video that Ben Min made, and we're walking down the row and looking at these misting nozzles spraying water up, and that water you'll be able to see it here in a minute. It will evaporate through the fruit zone. This is the heat wave we had in late July 2022. And you can see the effect that that misting system had on canopy temperature in the fruit zone. So fruit zone temperature peaking at 47. Here you can see the water misting evaporating up. There's a little bit of water on the vineyard floor. We have to yet figure this out because we don't want to compromise our water deficit in the soil. But the effect was very effective. 47 degrees Celsius peak temperature in the non-treated canopy, and 39 degrees. We were not able to maintain the fruit zone temperature exactly at 35, but 39 is much better than 47. With very little water use, about 1 millimeters per day. And then I don't have really time to go through this information. What I would show here is that the effect was that we had better fruit quality with the cooled system, and we had no negative effect. We had even bigger yield, we had bigger berries. This 2022 was a year, and 21 were years with very small berries, and winemakers even would have liked somewhat bigger berries. We were able to achieve that, and we got better bud fruitfulness for the following year. So we got almost 25% more clusters in the following year as the buds that were developing were being cooled as well. So higher yield, better acidity in the fruit and everything else, but no methoxypyrazine problems that winemakers were afraid of did not happen. We did not have more powder mildew, we did not have berry splitting, we did not have botrytis or any of that happening. So I'm going to move on, because I was going to talk briefly about vineyard nutrition as well, because we touched on that yesterday, and of course the problem is with vineyard nutrition that soils are so variable. Here we came up with a sand map for Washington. This is the state of Washington. The top 1 meter sand content across the entire state that we're mapping. And you can tell from this map that the sand content varies from about 10% in a vineyard to 100%. We have some vineyard soils that are 100% sand. Highly variable, even within individual vineyards, and that causes lots of issues with nutrient supply, because you will always have sections in the vineyard that are oversupplied and some that are undersupplied. And when you look at the table on the upper right, this is roughly how much we need per ton of fruit that is removed during harvest. It can be variable from year to year, but it's a small amount relatively. So this is what we need to replace as a minimum from year to year, but we don't want to oversupply nutrients, especially nitrogen, where we don't need it, and especially not on the sandy soil where it's easily leached out. So we did an experiment. A different postdoc, Tom Gronwald, did this experiment, a perlite experiment with lysimeters, tracking nutrient uptake of vines over an entire growing season, because we had previously been told, mostly by Australians, that nutrient uptake happens during bloom and post-harvest. What Tom found instead is if the conditions are not limiting, vines are able to take up nutrients over the entire growing season. So these lines, what you see here, is go from very low to very high nutrient supply. In ppm, I cannot translate this to how much this would be in like kilos per hectare or something, because it's a pot experiment. But the blue line is deficient supply, and the red line is massive oversupply of nutrients. And you can say that the vines are taking up these extra nutrients starting at roughly the 5-6 leaf stage. There's no nutrient uptake before that. So supplying nitrogen during dormancy or very early in the season is essentially wasting your money, because those nutrients will be leached out before the vines are even taking them up. But then they can take up nutrients through the entire growing season. But when you apply too much at any one time, the nutrient uptake efficiency decreases. You can see the blue lines, that at the end of the season, these vines have taken up 75% of all the nitrogen, in this case, that Tom supplied to them. The red line, the vines with too much N, had only taken up 34%. So 1/3 of the entire N that was applied to them they had taken up, the rest was leached out. And when there was a heat wave, like in the right-hand side, then uptake stalled before veraison during the lac phase and didn't kick in until the berries started to ripen. So the uptake efficiency dropped to 25%. Combination of hot temperatures and high nutrient supply, very low uptake efficiency. So the take-home message is here: supply nutrients at or after the 5-6 leaf stage, and supply them in small doses at any one time during the growing season. If you are struggling with yeast assimilable nitrogen, YAN, in your grapes, this is a PhD student of mine, Pierre Davadon, is doing this work, is finding that you can increase YAN by applying a small dose of nitrogen on the canopy. Foliar application of urea, in this case, at 15 kilos per hectare, is as effective under our conditions in Washington as 80 kilos soil-applied nitrogen to increase YAN, and has less of a negative effect on tannins and anthocyanins and so on. So you can supply low doses of nitrogen and increase YAN by correcting whatever is deficient at veraison by foliar applications of very small doses. And I'm going to run out of time, but we stopped a little bit late, right? So I have a couple more minutes. So cover crops, we're looking at cover crops yesterday. They evaporate water, they use nutrients, and you can maybe see, can you see a difference in front of this picture and the back? What's different? The size of the shadow, exactly, is different, right? What does that indicate? It indicates the size of the canopy. We have a bigger canopy in the front, lesser canopy in the back, and most of that is caused by the cover crop, in this case, evaporating water. This is an experiment we did in Australia many years ago, where we had cover crops over the entire vineyard surface in a hot climate, or just between the rows, or we sprayed everything out. So herbicide treatment across the entire vineyard floor, and we got these differences in canopy size, because the cover crop competes for water mostly, and a little bit for nutrients with the grapevines. So you can use cover crops to adapt your canopy size to try and control your vigor, but you have to be aware that cover crops evaporate water. So you can get more water stress if you don't control the cover crop. They also contribute to differences in soil temperature. You can see this is an infrared picture of the canopy and the soil. This is a dead cover crop, a summer dormant cover crop in Washington. and it looks cooler than the undervine strip. You can see the left-hand row is not being irrigated at the moment during a heat wave. And the row on the right-hand side, you can see the reddish dots at the bottom. That's from drip irrigation during that heat wave. And you can see a dramatic difference in canopy temperature, but also a difference in soil temperature, whether or not even a summer dormant cover crop is present. So cover crop is very good at cooling down the soil surface. And then I want to finish with something about yield, because we talked about yield yesterday. Yield versus quality is always the question. Most winemakers want low yields because they think there's a linear relationship between yield and quality. If you increase yield, you get better quality, and it's kind of what I'm showing here in the left-hand pictures: more berries per shoot, less sugar at harvest, because higher yield tends to delay ripening. But what was superimposed in this experiment was that the vines with the higher yield also were more vigorous and had more actively growing shoot tips during ripening, and that's in the right-hand side picture, essentially the same correlation that we see on the left with soluble solids, but now it's with actively growing shoot tips. So the more shoot tips you have growing on your vine during ripening, the more they compete with sugar accumulation in the fruit, and you're also delaying ripening. So again, hatching becomes important, but be careful with hatching. Don't let the shoots grow too long and the vine to spend a lot of energy in producing shoots, then you cut them off. It's sometimes more useful to cut off shoot tips repeatedly, but in shorter intervals, rather than waiting too long and having shoot tips that compete with vines. And then this, we touched on very briefly yesterday, machine pruning. You can obviously only do this in spur pruned or cordon trained vines. It's very difficult to do with cane pruned vines. Another experiment with this did with Syrah in Washington a few years ago. With machine pruning, you're getting bigger canopies, you're getting more water evaporation, you're getting higher yield, so a trend to delay ripening. But you're also getting, because of the bigger canopy, more dapple sunlight. You're getting less direct sun exposure of the fruit, meaning higher acidity in the fruit and ultimately in the wine as well. So we combined in this case, and I think this works, yeah. So we combine here machine pruning with machine thinning. We were adapting a mechanical harvester to run between approximately pea size and lag phase of the berries and just shaking off berries. You can see the ground speed, shaking speed here, and that worked extremely effectively. What we did not really know beforehand was that the mechanical harvester in this case was not really cluster thinning, it was berry thinning. So the added benefit of thinning this way rather than manually is that we're getting looser clusters. And any damage that happened on the berries that I was really afraid of, I was afraid we would get bunched in necrosis and all sorts of problems and botrytis from the damaged berries. That did not happen as long as the berries are still green and hard when you thin, and they will either heal or fall off. So no problem with ripening with machine pruning and machine thinning. And of course, then we can do machine harvesting if you want to fully mechanize the vineyard, because we can run a harvester at night. We don't have to just run it during the day as we normally do with hand harvesting. So this is one approach that we're trying in Washington to adapt vineyards to a warmer climate overall, is going full mechanization. We now have vineyards that are really fully mechanized. They do even shoot thinning by machine rather than by hand. And then I have one more results slide that I'm going back to varieties. We sometimes worry a lot about wine style with a particular variety not matching. For example, here, Chardonnay. Everybody wants to produce a Chardonnay that tastes just like in Burgundy. That is our ultimate goal. All right, so this is from a blind tasting that was done a few years ago in Europe. 12 Chardonnay experts, so these were people that worked with Chardonnay on a daily basis, producers or importers or sommeliers, so a very nice collection of experts on Chardonnay. They knew their Chardonnay. They all knew to tell a Burgundy from any other intruder Chardonnay. So they did wine tasting, 30 wines from 9 countries, 5 continents, price range when I converted it to US dollars, between $24 and $252. So big tenfold price range. And then they were on, this was published in a wine magazine in Switzerland and Germany, and they were honest enough to publish all their numbers. So now I can do statistics on those numbers and talk with my students about it. So of course I couldn't resist and did correlations between, okay, perceived origin. What did the judges say when the tasting was blind, where the wines were from? So here we have wines from France. They said were from France or California or Germany or Italy. They just couldn't tell. When they said the wines were from France, they were in fact from Australia, South Africa, Italy, Australia, Switzerland, Germany, France, California. They were from anywhere. So absolutely no ability of these experts that knew their Chardonnay to tell where the wines were from. So these are not just countries that are similar in climate and soils and so on. These are very different also in their production methods. And the Chardonnays were still pretty much the same. When you look at the correlation between price and tasting score, so they also ranked these. They gave them a score from 0 to 20. And of course, everything is between 16.5 and 19.5 when you do these kinds of ranking of tastings. And you can see there's no correlation. The most expensive wine, the California Chardonnay for $250, is sitting right in the middle of the pack in terms of quality score. One of the best wines they judged was a cheap South African Chardonnay that was at $24. So no telling of anything. That just means that some varieties are extremely adaptable. They can produce actually similar wine styles under very different climatic and soil conditions. But it matters what you do in the winery, of course, to those grapes. One more thing, the only significant result in this whole study that I found was when the judges thought that the Chardonnay was from Burgundy, they scored it higher. It didn't matter where the Chardonnay was from, they just had to think in their mind that that wine is probably from Burgundy, and they gave it a higher score. So that's how far wine tasting has come, but you as producers can control your wine style in the winery. And I'm going to finish by saying thank you to my team. This is where our irrigation water comes from in the Cascade Mountains. I take my team on a ski day once a year so that they see where the water comes from, and then I have to thank all the funding agencies and you for funding my travel. And because you're a captive audience, this is my book. If you want to buy it now, please do so. The 4th edition, as Debbie was saying, is supposed to come out next year. I'm submitting desperately during weekends material so they can publish the next version of the book. Thank you very much. I think we have some time for questions now.
Thank you very much, Markus. I love your data. Amazing amount of information you presented. Thank you very much. I'm Jim Wilworth. For those of you who don't know me, I'm an assistant professor here at in biological sciences here at Brock and a researcher at CCOVI. So I am going to moderate the Q&A session here. If you have any questions from the lecture today or the technical workshop from yesterday, what I have is a microphone here that I'll bring over to you, and that way everyone can hear your question. And with that, let's kickstart the Q&A period. Lots of stuff to talk about.
Markus, in one of your slides, you showed that 15 kilos of nitrogen applied through liquid under the plant is equivalent to 80 kilos of nitrogen applied to the ground. What kind of liquid fertilizer do you use for that?
Oh, thank you. Thanks. Should I talk? Oh, that's good. I can actually come closer. So for the soil applied nitrogen here, it was N32, UAN32 that we applied by fertigation to the drip irrigation system, and then the foliar nitrogen was urea. just urea, plain urea. But what I'm showing here, down here, this is actual kilos of N, nitrogen. Yeah. We also, just so to make that clear, we did not apply 15 kilos in one go. Under our conditions, this would lead to leaf burn in Washington. It's too hot, usually too dry. So we split it in 3 doses of 5 kilos each. All at variation, yeah, a few days apart. Yeah, starting at the beginning of color change, and then while color was changing, we would just apply 3 times. That usually, so if you do foliar application of fertilizer, it's usually a good idea to do a preliminary test to see how high you can go, so just so you don't burn your leaves off. Oh.
Yeah, we need it for the recording.
Oh, yes, you do. Even when the
Okay, so what's the weather like from veraison to harvest in Washington? I ask because research at Cornell has shown that applying urea in the latter part of the season to increase yan also increases susceptibility to botrytis.
So in Washington, botrytis is illegal. we don't have, well, we have it a little bit on Riesling and maybe on Pinot Gris, but this is Cabernet Sauvignon. Virtually never has botrytis. Most of our reds don't get botrytis. Many growers don't even spray for botrytis. They get caught in a really wet year, which almost never happens. But no, so far we've not seen any effect of even in pot experiments in the greenhouse, we've not seen botrytis appearing with foliar N. But that is a possibility. What we're doing now, the next step of this experiment that I'm not showing you, is trying to see if we can apply the nitrogen just on the leaves above the fruit zone, or should we target specifically the fruit zone? I agree with you that I was afraid of botrytis here too, because with these late doses of N, typically botrytis has a feast on them. It's possible here, first of all, that our conditions are too dry for botrytis. That's quite likely. But also maybe the dose isn't high enough in this case to really stimulate botrytis. I don't know that yet. But what we're finding is when we're applying the N on the leaves will translocate that to the fruit. It ends up with the fruit. If we apply it just on the fruit, it will stay in the fruit. So very little of it moves beyond the canopy. We'll see what happens with botrytis. There are some experiments from Switzerland that were published recently with urea at veraison as well, and they're not reporting big differences in botrytis either.
I'll ask you a quick a trick question then. So climate change can be very variable in terms of different regions, different years. What do you think is the greatest threat to grapevine production? Like you talked a lot about mitigation during the growing season and what we could possibly do. What would you rather see? Heat domes, polar vortexes, if you had the choice?
So that is a trick question because whatever I say, you're going to use it against me. So we're gonna go to British Columbia next, right? And if you ask them, they would say, well, absolutely, the winter is the problem, right? The summer is an issue, but the winter is a huge problem. And I tend to agree we have more problems with winter variability. In BC and my presentation there, I'm going to show some things about polar vortex and polar jet streams and things like that. The jet stream is that westerly wind that moves air from west to east across the globe. And it's becoming wobblier, so it has more excursions to north and south. That means we have more weather variability, more temperature variability during the winter. And that, of course, is a threat to production. If your vines are killed, you will have no yield, as the BC growers will tell you this year or last year as well. In the summer, you can change varieties. You can maybe switch to irrigation if it gets drier. You can do things to remove heat, like I showed you with this evaporative cooling system. You can do cover crops. There are things you can do, right, to mitigate climate change. In the long term, we're probably all going to change varieties that are better adapted. We're going to use more southern Italian, more Spanish varieties. We have more than 5,000 named varieties worldwide, and we're using, what did I show, about 40, maybe 50, really, for 75% of our production. There is a lot of scope to adapt in the summer. But whether those varieties are all resistant to winter cold, I'm not so sure about that. So that, I think the winter cold is the biggest threat overall. Nodding, so that's it.
I'm going to agree with what you're saying. Other questions, Kevin?
One of the big things that people think about is vine balance, matching crop yield to vine size to getting optimum maturity. I mean, it's always been a common thread of a balanced vine is a happier vine, and a happier vine is a healthier vine, and a healthier vine is a more durable vine. I mean, that's kind of the be-all, end-all. And I think from your, I don't know if you've done studies in looking at situations where vine balance has been tipped dramatically and what the outcomes were. An example being severely undercropping a vine to meet a certain parameter or overcropping a vine. Are the responses somewhat similar in those situations? And I guess, and how that would have an implication relative to, I'm thinking of winter hardiness and vine survival.
I don't know what happened to that picture just now. So this was one of those experiments that we thought we would change vine balance by mechanical pruning, right? And the original idea of the experiment was that we would have hand pruning and then machine pruning, and we would harvest, and then we would have a treatment that would thin the machine-pruned vines to the same level that the hand-pruned ones were at, thinking that the machine-pruned ones would be unbalanced, would be overcropped. That was the idea. And then we had an additional treatment where we would harvest everything based on bricks. So everything would be harvested at the same maturity level, or it would be harvested on the same day. So the machine-pruned, not thin treatment was going to be split into two, a late harvest and a standard harvest. And that never happened because we couldn't get that crop level so far out of balance that it really made a difference on ripening. That was one of the surprises here. Even with machine pruning, we couldn't crop the vines enough to make them unbalanced. We did another experiment years back with 3 different varieties. It was Chardonnay, Merlot, and Chenin Blanc. I hope that's not mine. With crop thinning, removing about 30% of the fruit. We did this for 3 or 4 years, I don't remember now, it was too long ago and I'm too old to remember things. There was no effect on fruit ripening at all. Of anything that we measured, it was the most boring experiment I've done in a long time, just no effect. We just couldn't get these vines to be cropped heavily enough to be out of balance. I tend to agree with you. I remember some data that Nick Ducouslian showed from Gallo years back, where they were looking at when Kevin is talking about vine balance, usually we mean yield to pruning weight ratio, right? We measure the crop yield and we measure something about vine size. We can measure leaf area or we can measure pruning weight. And a balanced vine is one that is supposed to have somewhere between a ratio of 5 to 10, somewhere in that range. And if it's below that, then the vine is supposed to be undercropped. If it's above that, it's overcropped. And Nick showed some data from California with data with vines that they had achieved within that 5 to 10 range, and then one treatment with up to 15 and one below that. And the overcropping did delay ripening and also decreased fruit composition. They made wine from these treatments, and it had the lowest flavor quality of all treatments. But the undercropped vines had the highest alcohol content. Of course, they ripened the most rapidly, and also poor flavor quality. So absolutely, vine balance is important, but it's very difficult often in our conditions to get the vines to get the idea to be overcropped that much.
Hi, Markus. Thanks for the nice presentation. Just changing the gears a bit, because we are talking about the sustainability, especially in terms of the grapevine production. I just wanted to take your idea on what impact of the Clean Plan program in Washington State. I know I have seen that when I'm doing my PhD days when Ken Eastwell was heading and now Scott Harper. I just wanted to take your, your idea on how it has impacted the grapevine production system in Washington State. And my second question is, like, is there any breeding program in Washington State? Is there anybody looking at the more sustainable varieties with the changing in the climatic conditions that are very frequent nowadays?
I could just get out of this by saying I'm a physiologist. I don't know anything about Clean Plan programs. But no, I mean, I used to run the Clean Plan program in Washington when I first started there. And without bragging, I think the impact has been quite dramatic because suddenly our nurseries, by having a Clean Plan program, and I'm assuming you all know what Sir is talking about when he means clean plants, is removing viruses and hopefully bacterial diseases if you do microtip propagation, or removing crown gall and so on from vines, and then you're passing that newly cleaned up material onto nurseries for propagation. And that's what we did in Washington as well. We brought a lot of selections in from Oregon, California, New York, and so on that we cleaned up by microtip propagation, and then made that material available to nurseries and enabled the nurseries to start new increase blocks, new propagation blocks in new locations. The problem was initially that they were replanting their existing blocks, and then all of our crown gall cleanup procedure was nullified because they had crown gall in the existing blocks already, and they were immediately reinfected. That was one of the biggest effects, eliminating crown gall and then going to new increase blocks. It has obviously also helped with virus diseases, especially leaf roll. That is the biggest one for us, leaf roll 3, the most important viral disease. The problem has become, so the program itself has been successful. Growers have been planting more clean material than they have previously, provided they were able to buy certified material from Washington certified nurseries. We went through a phase of expansion in Washington in the last 10 years. It stopped now, that we expanded on a rate of 10 and more % per year of new vineyard development. And it was too rapid for nurseries to keep up. And so growers would get vines from California that had not been tested or were propagated or propagated their own material. And then, of course, you lose all the benefit of the Clean Plan program. So it's important to work with your nurseries if you want to have a benefit of the Clean Plan program and buy material that is produced locally by local nurseries. And also, it's important to try and work with your neighbors. One of the big problems when you work with clean materials is if you plant your vineyard here with clean material, but the neighbor's vineyard next door has old virus-infected plants, you will get reinfected within 2-3 years. Very quick reinfection process happening, and then once you have it in your vineyard again, it will spread there through mealybugs and other insects. Breeding program, we don't have one in Washington. We have cherry breeding and apple breeding, but not grape breeding, which is not important enough in the world of wine to have our own breeding program. There is more breeding now happening in Germany, in California. New York has a big program now that might be beneficial for you. Missouri has a breeding program, but we're seeing a move. There's still traditional breeding overall, but we're seeing a move towards this CRISPR-Cas technology, where genes are being edited one by one in the plant. The first plant is now trying to be registered. The first Chardonnay is trying to be registered in Italy this year that was produced with this CRISPR-Cas technology. It's currently illegal in Europe. There's no legal, no way to legally introduce grapevines that way, but they're working on that through the European Parliament.
I'm looking at Barb, but we probably have time for one more question or so. Any other questions? Come on, there must be some questions from that time. Okay, what's your question? Okay, well, actually, I'll finish off with a question and see if anyone else has one after this. Is, you know, you started off with like the domestication of grapevines and the origin of vines. Are there some hidden gems, some silver bullets out there? You know, we look at Primitivo and how we have, or Zinfandel, and has origins from all over the world and might be more adaptable if you take a certain ecotype or something of a variety. You want to comment a little bit about that, just to kind of take things home?
Well, I should leave you by saying you should all plant Erkatsiteli. And simply because nobody can pronounce it, I can't pronounce it. No, there are probably hidden germs out there. There must be indigenous varieties in Georgia or Armenia or Azerbaijan that we don't know anything about. So it's a matter of, first of all, cleaning those varieties up. They're probably heavily virus infected by now, and we don't know how they would produce if they were free of virus. But if somebody could clean them up and start collections of these varieties, that would be wonderful to start evaluating how they perform. There's tons of varieties out there that we know next to nothing about. I don't have a specific example to tell you. I was just mentioning earlier Grüner Veltliner as a possibility because I've tasted very nice Grüner Veltliners in Austria. And I can see that in terms of climate adaptability, it might be a match for the Niagara Peninsula. There are other varieties out there that we just don't know. And it's the problem. I think what you're doing, in your case, collaborating with growers to do some of that, or what Bill Schenk, right, is doing, his own clonal evaluation in his own vineyard. To me, that is like where we need to go. It is impossible for us as scientists to evaluate all possible varieties that there are. It's just not doable. But if you do some varieties in your own locations and your neighbor does some others and you compare some, as long as you have at least one or two varieties that overlap, then you can directly compare notes. And that is what I would like our industry to do, what I would like your industry, if possible, to do. Do your own varietal evaluations and bring some exotic varieties in. So it will clean them up and make them available, and then you can go test them.
Any other questions? That's actually one thing that we're hoping to do with the new research farm, is we could take that risk and bring in some of these different clones, different varieties, and at least get some kind of knowledge.
So going back to the cleaning up the nursery stock, is it actually feasible to remove all known viruses and unknown viruses from the environment, right? Should we maybe be looking at varieties that are more resistant, or the effect of the virus isn't as consequential on fruit quality?
Grab the microphone. Thank you. Yeah, Jamie, what's up with that? So the short answer is no. It will never be possible to remove. And Sir knows this, right? You're smiling. It's absolutely impossible to remove all viruses. There's a bunch of viruses that we don't even know exist. So we cannot test for them. We don't know what to look for, right? And then there's the known viruses that are going to haunt us to the end of the day. We will never get rid of leaf roll virus. We will be able to clean up some of our vineyards, but then over time they will get reinfected again. There are varieties, I was talking with Seth about this yesterday. We have in our variety block that I was showing you results from, the 30 varieties that are replicated, different blocks across the vineyard. Spanking clean when we started, no known viruses in those plants. And then over a few years, we started to see leaf roll symptoms in here and there, individual plants. And ever since then, myself and my vineyard manager, we walk every row of that vineyard every year and tag each variety that we think has symptoms, and then we get it DNA tested for leaf roll mostly, and we rogue all the infected vines every year. And every year, even with roguing, we have new vines that get infected from vineyards that are around that have leaf roll virus. So, and when you think of conditions in Europe, for example, where you have a large vineyard, it looks really nice, but every single owner might own 3 rows of this vineyard here, and the next owner has 5 rows or 50 rows or something. You can replant your 3 rows all you like with clean plants. They're going to be reinfected immediately. So that is the problem. If we want to clean up overall, we need to look at this as an industry as a whole and take an integrated approach and maybe try to have entire regions that are trying to get replanted with clean plants. But no, we will never get rid of viruses completely. At least I don't see that. I don't think that's possible. Oh, resistant varieties. Sorry, we were talking about that too. And I was going to say, in that vineyard, I have never seen a Riesling wine that has leaf roll virus. I've never seen one in our vineyard that has any symptoms at all. And now Sid is telling you, oh, here we have symptoms in Riesling. You're saying the same thing. So is Riesling more resistant to leaf roll, or does it just under our conditions not show symptoms? I am very baffled right now. And the problem is I cannot afford to go and test every single vine in that vineyard. That would be way too expensive. But that's what I would have to do to find out. So maybe there are vines or varieties out there that are more resistant than others, but I don't know them.
Okay, one more question, and then if there's other further questions, we can talk later. So, who was it, Catherine? The other thing is that clonal related with Riesling? Are they the same clones? Yeah.
So there are a few growers that are using drip irrigation in Ontario, and there's kind of a bit of we've had some more dry years, and most of the growers, or some of the growers that are doing it, are monitoring soil moisture conditions based on like soil moisture sensors. But there's been some work looking at sap flow sensors and looking at kind of as alternatives to pressure bombs. I was wondering, what do you guys use out in Washington State, and what are your thoughts on that?
We do all of the above. So we have something I didn't show you anything about right now. We have a large project on artificial intelligence and the use of artificial intelligence in agriculture. In my involvement specifically viticulture. And as part of that, we have a vineyard that we call the Smart Vineyard that we outfitted with a bunch of sensors, a lot of sensors that we could find. It has soil moisture sensors, it has soil tension sensors, it has sap flow sensors, it has stem water potential, the embedded one, the FloraPulse one, embedded in the trunk sensors. We do leaf water potential measurements, pre-dawn, midday, and all of that. We have weather station equipment that estimates evapotranspiration from the vines. So we can correlate all these measurements together with each other. Many of them are correlated. The problem when you want to, so the ultimate goal in this case is to automate irrigation completely. So hands-off approach. The sensor measures how the vine feels and tells the irrigation solenoid to turn on or off. The problem is, what I see is that you can never rely on a single measure by itself. So let's say you measure leaf water potential or stem water potential in this case. That tells you how stressed or non-stressed the vine feels, but it doesn't tell you how much water you should apply. It might tell you when you should turn irrigation on, but not how long you should run it. A soil moisture sensor, on the other hand, may tell you how much water you have in the soil, and you can calculate from that how far can you bring it up. So it can tell you how much water you can apply, but it doesn't tell you how the vine feels. So you always, and the same goes if you measure evapotranspiration, you can estimate how much water to replace and so on, but it doesn't tell you what the vine is feeling. So usually you need a pair of sensors. one that measures the wine water status or something related to it, and one that measures either the soil water status or the atmosphere, so evapotranspiration, for example. Then the two combined, you can then potentially use to determine when to irrigate and how much to irrigate. But it doesn't work, no one sensor works in isolation. And right now I couldn't tell you this is the best sensor and this one you should stay away from.
Well, thank you very much, Markus, and thank you to all the audience members for all the questions as well. So this concludes the Ontario leg of the Triggs International Premium Lecture Series at CCOVI. So I'd like to also finish off with some thanks in addition to those that Debbie had mentioned, and as well as repeating some of these people. First, the Steering Committee and the Niagara Advisory Committee, chaired by Barb Tartarnik at CCOVI. The committee includes Alan Jackson, Matthias Openlander, Matthew Speck, Albert Seeger, Kevin Buis, Debbie Ingalls, and Kevin Kerr. So there's a lot of work that goes into this, and thank you very much to everybody. Also like to further acknowledge, and great to see you, Alan Jackson, who has supported and helped guide the lecture lecture series since its inception in 2004. Thanks again to BASF Canada for the support to make Triggs, again, a national one, heading off to BC. And we cannot forget, and we must acknowledge and thank Don and Elaine Triggs for their foresight in establishing the endowment that secures the lecture series for the future. As Debbie said yesterday, they walk the walk. Now, finally, before I invite everyone to enjoy the reception here, I'd like to thank Markus. Amazing time here, so insightful yesterday at the technical visits, and here again today, your wealth of knowledge. And it's been a long time to get you here. I was supposed to be here back in 2001, and the pandemic set everything back. So it may have taken us 5 years to get here, but I think everyone who has attended the last 2 days would agree that it was definitely worth the wait. Now, if you wouldn't mind coming up here, Markus, I have a small gift for you from all of us here. So thank you very much. Just a little piece of Niagara for you. It might be another Brock hat. Now, finally, what we're all been waiting for now is to have a little bit of fellowship, and we could talk further with Markus and amongst ourselves what we learned, and join us for the reception here. We have wines that have been graciously sponsored by Henry of Pelham, so thanks again to Matthew and the rest of the Speck brothers for supplying wines. We have wines from Henry of Pelham, and also I'd like to thank Shiraz Mortier, as Malivore is also sponsoring our reception here, and we have wines from both of these Ontario wineries. And with that, we'll see you again in 2 years. Hopefully it's 2 years and not another 5, and for the next installment of the Triggs lecture series. So thanks again, everyone, for attending and for being part of the technical visits yesterday as well. And thanks to all of our hosts for that. So let's have a couple glasses of Ontario wine.